Here's the complete solution to the draining tank problem that you guys have been looking at in various forms for a little while. So we have a tank. This is the first one you got, I think. It's a full of kerosene. It's got a height of 4 meters. It's a cylindrical tank. It has a diameter of 2.5 meters. And it's got an outlet right on the bottom. And the outlet diameter, the diameter of that hole in the outlet through an outlet valve is 5 centimeters. So you're asked to find three different things, two of which are pretty easy and one of which is a little bit harder. You're supposed to find the mass of the kerosene in the full tank. That's extremely easy. You're asked to find the instantaneous volumetric flow rate when the valve is opened. That's also pretty easy. And then you're asked to estimate the time for the tank to drain to 3/4 capacity. And that's harder because as the tank drains, we'll see that the velocity decreases the velocity with which the fluid comes out because the pressure decreases as it becomes less and less full. The pressure at the bottom of the tank decreases. All right, so let's go ahead and take these on one at a time. The first part is very easy. We're going to find the mass of the kerosene, and all we need to do that is find the volume of the tank and multiply that by the density of kerosene. So the volume of the tank for a cylinder, we have pi d squared over 4 for the circular area on top, and then we just multiply that by the height of the tank, which is 4, and that's all in meters. Hopefully, we will use meters for everything. The D, of course, we were given was 2.5 meters. So when we plug all of that in, we get that the volume is equal to 19.6 meters cubed for that cylindrical tank, and then we can multiply that by density, and we get that the kerosene mass is 15,758 kilograms. So quite heavy. 19 cubic meters of kerosene is a lot. And so there you go. All right, so now we want to do part B. Part B is a little bit harder. We have to consider this tank, and there's a jet of fluid coming out here, and we need to consider how fast everything is going. In order to do that, we need to assume that the pressure at the top of the tank is atmospheric. So we'll say that P1 is standard atmospheric pressure, 101,000 newtons per meter squared. And as you go down in the tank, of course, we're going to have more. There's not, assuming this valve is a very simple valve at the bottom, we can treat this as a Bernoulli problem, assume that friction effects are negligible as it just shoots out this hole. So we're going to go ahead and use the Bernoulli equation, P1 over rho plus V1 squared over 2 plus GZ1 is equal to P2 over rho plus V2 squared over 2 plus GZ2. And we just need to define some kind of points here. So we're going to say that point 1 will be up here at the top where the fluid is really not moving and the pressure is 101. And so we can say the pressure is 101 there. And the pressure at 2 is the outlet pressure. So this is going to be our P2 is P out. But our outlet pressure is also atmospheric because jets that are being freely released into the atmosphere cannot exceed atmospheric pressure. They cannot maintain a pressure difference unless they're going supersonic speeds, and that's only for air, I believe. So at any rate, it's going to be P out is going to be also atmospheric. So P1 and P2 are going to be the same. They're both going to be P naught. So we'll go ahead and write P naught here just for thoroughness. P naught over rho. And we got V1 squared over 2, GZ1. And then we've got P naught over rho plus the outlet velocity squared over 2 plus GZ2. All right, so that's that. The P naughts are going to, these P naught terms clearly cancel. V1 is 0. So we're going to say that, this is, when you, first of all, when you spontaneously open this tank, it's going to, this water's going to start shooting out. This water here, or this kerosene is going to be going very, very slowly down. But that is negligible. You got a large tank of kerosene, this jet of water coming out. This velocity is going to go very, very slowly down. So this is going to be negligible. It's not truly 0, but it's almost 0. So we're left with that the velocity out can be estimated as, and estimated very well as, 2 times g times, we have z2 minus z1, it looks like. Sorry, z1 minus z2 makes more sense. And there's our velocity estimate. So that's for velocity squared, of course. So we know z1 minus z2, the top of the tank is at 4 meters. We know it's 4 meters tall. So we can say, all right, that's going to be that the outlet velocity squared is going to be 2g times 4 meters is the difference between Z1 and Z2. So that's it. We plug in our 9.81 for our gravity, and we can get a V out. So V out comes out to be, by that calculation, 8.88 meters per second. So that's our V out. What we're asked for is a volumetric flow rate. So we need to take that V out and use it in a volumetric flow rate. So Q dot, the volumetric flow rate, is the area times that V out. And so the area, of course, we now have to calculate. That's the area of the valve hole. The hole of the valve is, is circular. We were told that the diameter of that hole was 5 centimeters, so we can use that. 0.05 meters squared over 4 is the area of that hole. So that comes out to be 0.00196 meters squared, we think. And so now we're going to, I'm going to double check that just to make sure I didn't do something weird there. So 0.05 squared divided by 4 times pi. Yeah, 0.00196, that's fine. Meters squared. So that's good, and then we just take that and we multiply it by this V out of 8.88 meters per second, and we get that Q dot is equal to 0.017 meters cubed per second. So that's the answer to part B. All right, so now we have to do part C, and clearly part C is by far the hardest. Most of you have been able to do parts A and B, hopefully, and you have all been able to do them actually. That would be nice. But anyway, part C is definitely harder. So now we're trying to estimate the time it takes to drain the tank by down to 3/4. So we're going to try to get from the height of 4 meters of that fluid down to 3 meters. The way to do that, you have to come up with an ODE because the Q dot is going to depend on the time, and it's going to depend on the time because this velocity depends on this Z terms, and the Z1 is going to start to change as the tank drains. Z1 is going to decrease, so our velocity is going to change and it's going to go down. So that's going to change our Q dot. So we can't just we're going to have to figure out how that is related. So the volume that's left is going to be 4 times the cross-sectional area of the tank. I'll call that CST, cross-section tank, minus the integral from 0 to some time of Q dot, which is a function of time, dt. So that's a true statement. That says that if you integrate the total volumetric flow over time as a function of time, and this is the total volume of the tank initially, and you're subtracting how much is drained out. So this volumetric flow rate is what's draining out. It's changing with time, and we can integrate it from some 0 to some new time, and that will get us the total volume left. So this is the volume of kerosene, not the volume of the tank. The volume of kerosene in the tank is related like this. All right, so for a CST is equal to the cross-sectional area times Z1, of course. So we have A CST Z1 is the total area in the 4. This is this area, so that Z1 is 4 minus 0 to t Q dot dt. That's pretty trivial. So we just replace this 4 with Z1, which we know is 4, just so we can see its dependence. And so then we're going to say on the left that this is a cross-sectional times Z. So whatever Z is, that's going to be our height of the fluid at any given time. And then we have equals A CST times Z1, which is the 4 value, minus the integral from 0 to t of Q dot over t. Q dot dt, like that. And so if we want Z as a function of time, we would say Z, we can divide by A CST. We get the initial Z1 minus the integral from 0 to t of Q dot over A cross-sectional area, where we've divided by that on both sides. This Z1 is 4, of course, so I'm going to go ahead and put that in. So I have Z equals 4 minus the 0 to T Q dot over A cross-sectional T dt. All right, so that looks good. Now I'm going to take dz dt. So I'm going to take the derivative of both sides. The derivative of z is dz dt. The derivative of 4 is 0. The derivative of the integral is just what's left in the integral. So CST there. So that's my ODE. So there's my ODE. And now I'm going to relate Q to time. So I'm going to say Q, which is a function of time, is equal to the outlet area times V out, which we know. So we have that, we knew that from before. We already used that, so that's our relationship for Q. And V out, we already calculated, was equal to 2GZ. So it depends on Z. So that's our relationship for Q. And so we can put that, we can rewrite that using the Q dot. So Q dot equals A of the outlet times the root of 2GZ. All right, and then we take that and we plug it back in up to my ODE. So I've got dz dt is equal to minus A out root 2GZ divided by A cross-sectional of the tank. All right, that looks pretty good. And now what I can do is integrate that expression. So that's what I'm going to do. I have dz dt is equal to this stuff. I have a z on the left. In order to integrate it, I need to put all the z's all together. I need to put all the t's all together. Well, there aren't any t's, but I need to separate the t's and the z's. So I'm going to have, on the left, I'm going to have, bring over that root of z. So I'm going to have 1 over the square root of z, dz on the left. On the right, I'm going to have A out over A cross-section of the tank. And then I'm going to have 2 root 2g and then dt. All right? So that's my separation of variables. Doesn't matter which side you put the constants on. These could go on the left or the right. Doesn't make any difference. They're not going to matter. What's going to matter is you have to have the z on this side over here. All right, so now I can integrate both of those things. So there's my integral. So this is z to the negative 1/2 power. So z to the negative 1/2, if you take that integral, it's 1/2 z to the 1/2. And that's the integral on the left side. On the right side, everything's a constant except dt. So that's just going to be all that stuff times 2 times t. And of course, I have to put in a constant of integration. So there's my constant of integration. All right, so that's what this looks like. I have basically I have the answer. I'm going to multiply both sides by, oh, I'm sorry, this is wrong. This should not be 1/2. It should be 2, my bad. It's the integral of z to the negative 1/2 is 2 times 1/2 because that 1/2 is going to come down. So there we go, that's correct. So we have 2z to the 1/2 equals all this stuff. I'll divide both sides by 2, and that'll just put my z on the left there. So I've got z to the 1/2 on the left, and then I have minus A out over A cross-section of tank, and then I have the 2g root divided by 2, so that's the same as root g over 2. And then I have, I didn't make that dt, it's supposed to be t plus c. All right, that looks good. All right, so now we've got that. Oh, I guess this would be c over 2. So that goes there. Now, let's apply our initial condition. Our initial condition is apply initial condition. Z equals 4 at t equals 0, because that's where we started, right? When we started, the tank is full, the kerosene level is 4 meters. So we go ahead and put z equals 4 in there. We get 4 square root of 4 is equal to A out over AS CST times root g over 2 times t, but t is supposed to be 0, so that's just 0 plus c over 2. So the square root of 4 equals c over 2. Square root of 4, of course, is plus or minus 2. So equals c over 2. So c is equal to plus or minus 4. So that's our constant of integration, is c equals plus or minus 4. I'm going to plug that back into my solution. So that goes here. So z to the 1/2 is equal to minus a out over a cross-sectional area of the tank times g over 2 plus or minus 2. That's 4 over 2, right? So that's my solution. Now all I have to do is plug in, oh, I left out the t. It would work a lot better if I didn't drop terms. T plus or minus 2. Let's see, that has a t in it. So, all right, so that's my solution. And now all I have to do is solve this for z is equal to 3. Find t when z equals 3. Plug in my a outs and my a CSTs. My a out, I don't think we did find a out earlier. Let's see what we found for that. We had a out was equal to something small, 0.00196 meters. So z to the 1/2 equals negative 0.00196 meters squared over the cross-sectional area of the tank. Did we calculate that already? I don't remember. Maybe not. So we'll just do it again. ACST is the diameter of the tank we said was 2.5 meters. So we got 2.5 meters squared over 4 times pi. 2.5 squared divided by 4 times pi is equal to 4.91 meters squared. So we have a big difference between the two areas. 0.91 meters squared there. We do that again just to make sure. X squared times pi divided by 4. 4.91. Yep, I always hit everything into my calculator at least twice, because I hit enough mistakes that that's worth trying. So I got that, and I got my g over 2 square root, so that's 9.81 over 2, and square root that, and I get 2.21. Let's put the 2.21 in. 2.21 t plus or minus 2. All right. Well, it looks good. So I put in, finally, on the left-hand side, I put in the 3 that I'm shooting for. So 3 to the 1/2, that's the height of z that I'm after, is equal to, when I do this math out, I get minus 3.99 times 10 to the minus 4 times 2.21 plus or minus 2. And that's still with a t. And I want to solve that for t. So I solve that for t, and let's see what I get. I get 3 to the 1/2 is just 1.73, and then plus or minus 2, I got to decide this. So I'm either going to add or subtract this. Well, I need t to come out to be positive, because I'm going looking forward in time, not backward in time. So if this is on the left is 1.73, I need to, if I subtract 2 to that will cause this to be a negative, and that will be negative and negative, so it'll give me a positive t. So this is going to be the positive 2 here. If it were a negative 2, then it would add up, and this would stay positive, and that would give me a negative time. So if I bring that positive 2 over to the other side, I get 1.73 minus 2 in the top, divided by 8.82 times 10 to the minus 4 in the bottom. Of course, that's negative over negative is going to give me a positive, so I get t is equal to negative 0.268 over negative 8.82 times 10 to the minus 4th. And when I crunch that into my calculator, I find that the time required to drain the tank down to 3/4 capacity is 304 seconds.